Hello dear learners, welcome back to our today's video lecture. As we already know that we are dealing with the analysis of continuous beam by the application of Clapeyron's theorem of three moments. Now today we are going to take another numerical which is based on the continuous beam, of course, but in this case one of the end will be made as fixed. Let us see what problem we have to analyze today. So here in this problem we can see in this figure number 1 we are having a continuous beam which is supported at A, B and C, but here at point A it is made as a fixed support, whereas at point B and C it is a simple support. Now this is going to make a peculiar case of analysis of a continuous beam only due to the existence of this fixed end about point A. Another characteristic of this beam is the moment of inertia is different. Here you can see for the span AB the moment of inertia is equal to 2I, whereas for BC it is equal to I, and the spans are, here we can see for the first span length is equal to 6 meter and for the second span length is equal to 4 meter, where we have a point load exactly acting at the center. So when this particular fixed end we are going to come across, different sort of analysis is to be adopted for this particular type of a problem. Now let us see what we can do it with the fixed end. Now in this figure number 2 we can see I have simply extended one dummy span on the left hand side of this particular A point. So this OA is a dummy span having all the parameters as dummy or equal to 0. Here you can see the length I have considered is equal to 0 meter and rest of the things are as usual, only with the difference that we have extended a dummy span on the left hand side of point A. So this is what we have to do initially. Now the standard methodology is one and the same. The very first thing which we have to do in this case is to draw the free bending moment diagram, as we used to do since long time for the fixed beam analysis. Also we used to do the same thing. Similarly for this particular analysis of continuous beam we have drawn the free bending moment diagram. Now we remember what is the governing equation of a three moment theorem. So here I have shown that, but certain specific values are needed to be initially worked out from the free bending moment. So here you can see I have worked out the value of A0 and X0 which are needed in this particular governing equation of Clapeyron's theorem. So A0, no loading, so no bending moment, so no area of a bending moment. Similarly X0, as L0 itself is equal to 0, so X0 will be also equal to 0. As far as the second span is concerned, the area of free bending moment for the second span AB is equal to 360, and this is how we have to work out the value of A1. We know this free bending moment is coming out to be equal to parabola, and we know what is the area of parabola, 2 by 3 base into height. So base is 6 and height is 360, and this is 360 we can work out as usual what we used to do for a free bending moment of any of the standard case. Now x1 is concerned, as far as the x1 is concerned, it is to be measured from point A, and that is coming out to be equal to 3. X1 is equal to 3. Why it is equal to 3? Because this being a symmetrical figure, so x bar of this or x1 distance of this first area A1 is going to act at the center. Now either we measure this x1 from A end or B end, it is going to be equal to 3. But usually as a practice, usually we find out the value of x1 and x2s about the center of the span under consideration. So here the span which we are considering is 0 AB, so about center the value of x1 is equal to 3. Similarly A2, when it comes to A2, which will be used, these values of A2 and x2 are used in the next what we can say application of three moment. So initially at this first span OAB, value of A0 and A1 are required to be worked out. So that we have worked out in this particular slide. Now second job is to apply the three moment theorem to the span under consideration, that is OAB. So we know the governing equation is this. So here one more understanding is very much required here. Here M0, that is nothing but it is the bending moment about point O. This is a simple support, and another bending moment, that is MC. This is another bending moment at another simple support C. So at extreme simple supports, we know the bending moment has to be equal to 0. That's why we have seen here M0 is equal to 0 as well as MC is equal to 0. Why it is so? Because these are the two extreme supports of this continuous beam where the bending moment has to be equal to 0. That's why M0 is equal to MC is equal to 0. Now moving ahead, we can see here the same figures for the original extended dummy span beam and the free bending moment. Now we are going to put the values what we have already worked out. So here M0 is 0, so 0, L0 is 0, so 0. So first term is going to be equal to 0. Now as far as this 2MA L0 by I0 plus L1 by I1 is concerned, put the appropriate value, you will be getting 0 plus 6 by 2i. Here no need to mention 2i is coming because for the second span AB the moment of inertia is equal to 2i. Similarly MB L1 by I1, L1 is already known to you, that is equal to the value of 6. Is it okay? So putting all these values on the left hand side of the governing equation as well as on the right hand side and doing the simplification, we are coming across a new equation which is equation number 1, that is 2mb plus, sorry, it is 2ma plus mb is equal to 180, calling this as equation number 1. So make a correction here, 2ma plus mb is equal to 180 as equation number 1. Moving ahead, we have to consider the second span, that is AB and BC. So already we have concluded bending moment at point C has to be equal to 0. So here we are going to apply the Clapeyron's theorem, that is three moment theorem here. So here we are having the governing equation of Clapeyron's theorem for the appropriate spans under consideration. Now putting the value of Li and A1, A2 in this particular governing equation, we get this particular simplified form, and again simplifying that, you are going to come across a new equation, that is 3ma plus 14mb is equal to 780. Call this as equation number 2. Now we know we are having two equations, and how many unknowns we have? We have two unknowns, ma, mb, ma and mb. So after solving these two equations 1 and 2, you will be getting the values of this ma and mb. So here you can see we have solved this equation number 1 and 2. Again 2ma plus mb is equal to 180 and 3ma plus 14mb is equal to 780. So after solving these two simultaneous equation, we are coming across the value of ma and mb is equal to 69.6 kilonewton meter. It is coming out to be hogging, obviously it is minus, so mb is equal to 40.8, again hogging, again it is going to be minus. Now after finishing with this, as we know what we have to do is we have to draw the various bending moment diagram which we have already drawn. So here it is free bending moment diagram for span AB and BC. We have not considered a dummy span here because everything for this dummy span was equal to 0, so no need to show that particular in this particular case. Now second, the friction moment at point A, B and C are being shown. At A it was coming out to be minus 69.6 kilonewton meter. So here I have shown, it is very obvious that this figure itself is going to be minus because all the values are hogging. So at point B we have got the hogging bending moment equal to 40.8. Now once we come across these two bending moment, one is free bending moment and a friction bending moment, now we have to superimpose these two bending moment. Now again no need to say that this line is going to act as a neutral axis where the bending moment value should be equal to 0. So below that are negative and above that are positive. So this is going to be the resultant bending moment acting at the appropriate point. Is it okay? So this value minus this value will give you the resultant bending moment at the center of this particular span. Similar is the case with the another span BC. This is going to be the resultant bending moment about the center. So this is how we have to analyze when it comes to one of the end as a free end. So in the next class we shall be dealing with another numerical which is to be analyzed. In this particular case there will be one fixed end and the other, on the other hand there will be a overhanging. So this is also one of the interesting numericals to be understood. So in the next class we shall be dealing with this particular specific type of a problem in which there is one fixed end and on the other hand there will be a overhang. So this is what we have for today. Thank you very much.